Hi, my name's Nicole Fry, and this is Lab 5, the Human Rocket. Felix Baumgartner is a skydiver who has jumped from the highest point of the sky, also known as the stratosphere, while he was at 38,969.4 meters over the Earth's surface. This same jump also titled Felix as the first skydiver to also go faster than the speed of sound, where he reached a maximum velocity of 833.9 miles per hour. The purpose of this lab is to observe the motion of Felix. In this lab, he'll be considered a free-falling object, initially at rest, and his descent into free-fall flight that broke the sound barrier. The goal is to understand through computational modeling and comparison the forces acting on him, the system, and to analyze the effects of temperature and air density on his falling trajectory. The overall objectives are to create an appropriate model for air resistance for an object in freefall with conditions that describe Felix's record-breaking freefall. Also, an objective is to use GlowScript to create a computational graphical model of his position and velocity, and then to also discuss the effects of air density and temperature on the physics of Felix's freefall. The physics principles being used in this lab consist of Newton's second law, or also known as the momentum principle, in both an analytical as well as computational sense. As mentioned earlier, Felix Baumgartner fell from the height of 38,969.4 meters, which broke the sound barrier without the help of an aircraft. To the right, you'll see a diagram of Felix's freefall. Taking this into consideration, listed on this slide are first off the max vertical speed, which was 377.1 meters per second. The time of the max vertical speed consisted of 50 seconds. The time of freefall consisted of 4 minutes and 20 seconds, which is 260 seconds. The parachute was deployed at 2,567 meters above the ground. The minimum temperature experienced at 18,203 meters was 202.1 Kelvin. And then the weight of Felix was 117.934 kilograms. Some system reference assumptions that had to be made was first to assume Felix to be a point particle system model. Also, once we can consider him simply a point or an object, the object starts from rest, and therefore its initial velocity is at the vector 0,0,0 meters per second. And then also the object drops from above the x-axis at an initial position of 38,969.4, 0 meters. Something to also note is that the sound barrier is not a speed barrier, but a way to indicate the speed of sound, which is dependent upon temperature and the density of air. So in order to model the drag for the system, I use the equation 1/2 rho times v squared times c sub d times a, which equals mass times gravity. For v, I use the max speed achieved, which was 377.1 meters per second. For rho, I found it by using an online calculator and inputted the height at which the maximum velocity was achieved and got the corresponding air density. I solved for c sub d times a, which I use as a coefficient b for the drag force in the code. In order to calculate the change in air density, or rho, in the code, I use the equation P equals P naught times 273 divided by temperature times e to the negative P naught times g times h over capital P naught. In order to change temperature, I used both the starting and final temperature that Felix experienced during his freefall. This was found using an online calculator that gives you the average temperature at the corresponding altitude. So I had that delta T was equal to 271.4 minus 248.164 divided by 260, and that gave us 0.08 Kelvin. Basically, I found the difference in temperature and then divided it by the total time, which was the 260 seconds. It's important to note that the temperature does not change linearly, as shown by the graph on the right that was found on the internet, and this discrepancy is taken into consideration as I proceeded through the lab. The initial conditions, I inputted the mass, the initial position and velocity, the change in time and change in temperature, the initial temperature, lowercase p naught, which is the air density at sea level, capital P naught, which is the air pressure at sea level, the magnitude of the weight force g, and the coefficient of drag that was calculated previously. This is all shown on the screenshot to the left. Inside the while loop, which is shown to the right, I put the equation that updates rho and then defined the forces acting on the system, which consists of the force of gravity, or F-grav, and then the force of drag, which is also known as air resistance, and in the code is denoted as F-drag. Also inside the while loop, you have the position and velocity update equations that are based off of Newton's second law, or the momentum principle. And then temperature and time were also updated inside the while loop as well. When the program was run, it gave me a position versus time graph as well as a velocity versus time graph, which is then used in the analysis portion on the next slide. In the results, the graph shows the final position to be 2,233.35 meters. However, in reality, Felix's final position in free fall, where the parachute was deployed, was 2,567 meters above the ground. The graph also shows that the maximum speed reached during free fall to be 308.878 meters per second, when the highest speed Felix actually reached was 377.1 meters per second. These discrepancies could be attributed to both the inaccuracy of the temperature model in the code, which in turn would cause an inaccuracy in the air density calculation through the iterations. Also, lastly, Felix did break the sound barrier at 309.7 meters and at 34 seconds into the free fall, and this is possible. This is accurately represented in the graph to the right as it illustrates that sound travels at lower speeds and higher altitudes. This could be explained because sound requires a medium through which to be able to travel through. So at higher altitudes, your particles are spread further apart. Because of this, it takes longer for the sound vibrations to travel through particle to particle, therefore having a smaller velocity than it would closer to sea level.